in our approach, we adopt a centralized approach, which means that for sensors, they just need to observe each other's behavior. And if there's something wrong, they just need to issue alert to the base station. All the reasoning is done by the base station, not by the sensor. Okay. So here's the basic components of the proposed framework. So first, we have the observability graph. So this pretty much represents the relationship between the sensor nodes who can observe whose activity. Okay? So V is a set of nodes whose integrity we care about. Okay? We may not care every node's integrity. We may just care a subset of them. Okay? And one edge from S1 to S2, if only if S1 can observe the behavior of S2. And S1 may issue an alert against S2 sometimes. Okay? And the second component is alert. So we model alert as a tuple which composes of 3 values. First one is the time the alert is issued. And then who is the issuer of the alert, S1. And who is the target of the alert, which is S2. So which means that at time t, S1 issue an alert against S2. So we may further enrich this alert to include more information. For example, how confident S1 is about the alert. But for simplicity, we just have these 3 values here. Okay? And note that a sensor may not be perfect. Even though a sensor is not compromised, maybe because accuracy of the sensor, it may not always report the 100% accurate information. Okay? So here we use a sensor behavior model to model the sensing quality of a sensor node. So similarly, we depend on detection mechanisms, and the detection mechanism may not be perfect. Okay? So it may also make some mistake from time to time, even though nothing is wrong with the system. So we're using observer model to model the possibility that detection mechanism giving you some wrong answer. Okay? So the next parameter is called security estimation. Basically, this is the upper bound of the compromised nodes in the system. So obviously, if all the nodes can be compromised, then there's no way you can detect which node is compromised. So we assume that somehow the application can get an upper bound of the number of compromised nodes. Okay. Finally, we have one component called application identification function F. So given all the above information, this function is going to give me a list of sensors which we believe is compromised. Okay. So let's look at an example that how we can using the framework to model some sensor applications. Okay. So one application is sensor network localization. Okay. In many applications, it requires that we know the location of a sensor. Okay. For example, if you're talking about event tracking, I need to know that where the event happened. So I need to know not only that there's some event happened, I also need to know the location of the sensor node. Okay. So it's very expensive to equip a localization device on every sensor node. Okay. So one basic approach is that we have some beacon nodes in the network. Those are those sensor nodes who knows their own locations. Okay. Maybe they have some GPS device equipped with them. And for the other sensors, they're going to talk to the beacon nodes nearby to get some location references. Okay. So from those location references, I can estimate or derive my own location. Okay. But the problem is that if one beacon node got compromised, the beacon node may just claim arbitrary location. Okay. Then cause other sensor nodes to derive their location forcefully. Okay. So in 2005, Liu et al. Proposed one detection mechanism for compromised beacon nodes. So the basic idea is that they try to let beacon nodes nearby to probe each other. Okay? I know my own location, but I pretend that I don't know my location. I talk to some other beacon node. Then I compare the measured distance between the two sensor nodes and the derived distance between them. If they are very different from each other, then I know that the other beacon node is giving me wrong location references. So I may issue alert to the base station. Okay. So clearly, if a beacon node is compromised, he may also just say that the other beacon node is compromised and issue alert. So how are we going to model this sensor network localization service by using our framework? Okay. So here I show one deployment of a sensor network, and the rectangle nodes represent beacon nodes. They know their own location. And the circles represent those common sensor nodes. Okay. Yes?
This may be a very silly question, but are the beacon nodes fixed?
You mean fixed mean the location is fixed? Yeah, usually we assume it's a static network, so once you deploy it, you just stay there. Okay. No, they don't move, the static network. Okay. So in this case, we see that, for example, S2 may get location references from B1, B2, B4, and B3. Okay. So here we cared about the integrity of beacon nodes. So in our observability graph, we may only have beacon nodes here. So we have edges between B3 and B4 means that they may probe each other. Okay? B3 may try to probe B4 to see whether they're given the right location. Okay? Now how about the sensor behavior model and observer model? So those are all related to the accuracy of the distance measurement. If the distance measurement is not accurate, then you may have a not accurate observer model here. Okay, those are application specific. And the security estimation can also be determined by the application. Okay. So now suppose we're talking about localization, and now the base station received a bunch of alerts. So how can I know which beacon node is really compromised from those alerts? Okay. So because beacon nodes are not perfect, if you only receive one alert, it may not mean much, right? Maybe it's just an innocent mistake. But if during one period of time, I received excessive amount of alerts from node S1 to node S2, then I know that probably there's something wrong. Okay, and so we call such edge abnormal edge. That means that during this period of time, something wrong between this pair. From this abnormal edge, I cannot tell which node is bad. Maybe S1 is bad. S1 just issues a lot of alerts against others. Maybe S2 is really bad. S2 gives a lot of false location reference. Okay, but I can know for sure that at least one of them is bad. Otherwise, there should not be so many alerts between them. Okay, so we also call it a suspicious pair. Means that given this pair, I know for sure at least one of them is bad, is compromised. Okay, so obviously this is one situation. I know there must be one of them bad. So in another situation, suppose S1 and S2 are observing the behavior of the same node S3. But S1 thinks S3 is good, but S2 thinks S3 is bad. Then I know that one of S1 and S2 must be bad. Otherwise, this should give me the same consistent evaluation of S3. Okay? So we can identify suspicious pairs by based on these two conditions. Either you have issued a lot of alerts between these two pairs, or you have different assessment of the same node. Okay. So by collect all those suspicious pairs, I can construct an inferred graph, which is basically composed of all the suspicious pairs. Yes?
Is it possible for a bad node to report correct information to one node, but incorrect information to another?
That's possible. That's possible. So let's look at it.
So is it possible that S1 is issuing that abnormal edge because it can see more information compared to what S2 can see?
So that should be reflected in your observability graph. So if you can observe another node's behavior, then there should be edge between S1 and the other node.
But that model, it models it at 1 or 0, observe or not observe. Mm-hmm. But maybe you can observe to 90%. Like if you are very close to a sensor, you can see it better, or you can see more of the traffic.
Right.
But if you are farther, you can't see much traffic. So.
Yes. So it's possible, but in that case, you have to enhance